Okay, so hi everyone. So good evening. Welcome back to Plan 252. Okay, transportation modeling. Okay, this is the agenda for today. Hope you can see. So we have discussed about introduction to urban transport planning. Okay, and uh, last meeting we discussed a little bit about linear regression. So we will continue that. Okay, into nonlinear transformation and the matrix. Okay. Then we'll discuss about fundamental traffic flow, okay, with the purpose to show you the model for congestion travel cost model. Yeah. And then if we still have time, we continue with introduction to transport policy, IFN transport and policy analysis. Yeah. Okay. Okay, so let's go to the first part. It is E2P. So you can follow this in Moodle, okay, in Revoledo to our screen. Okay. So this is what we discussed last meeting. Okay. We have done all of this, right? No, until here probably. Yeah. So and today we'll discuss this part, yeah, about the linear regression, which in general is inverse, okay, and nonlinear regression. Okay. Now, I ask you to review. I hope you still remember. I ask you to review the power rules and logarithm rule. Okay, and today we will discuss about nonlinear transformation. Okay. Uh, yes, I know in Excel you can do certain model, yeah. For example, a power model, exponential model, and so on. So, but we can also transform many other models which is not in Excel uh, automation, right? So let's start with the first one, okay, power model, something like this, okay. Y is equal to A times X exponent P, okay. So if you have this kind of model, how are you going to transform this into a linear model? Okay, let's take this in the notepad. So I will open a notepad. Okay, hey, let's find a new window. Okay, okay, so can you see this? Is it too small? So our model is y equal to a times x exponent p. Okay, exponent p. Okay, so if you take logarithm to both sides, so you will have log y, okay, equal to log of a, right, multiplied by uh, x exponent b, isn't it? So, but based on logarithm rule, okay, if you have log of a multiplied a x exponent b, yeah, so this is the logarithm rule. So if you have if you have a multiplication like this, okay, and you can add, okay, you can separate them, okay, by addition of log. The same thing if you have exponent, okay, the exponent can go out. Can you see this? Okay, so that uh, so the exponent can go out like this. Yeah. So in that case, the same thing. So we just copy this. Equal to, now you have log A plus log A x exponent B, isn't it? But the exponent can go out. Okay, so I will copy all of this. Okay, so now the exponent go out here. B, okay, now multiple of log x. Can you see that? Okay. Now, if you look at this, we can substitute log x with the new variables. Okay, so let's call this capital Y is equal to log Y. Okay, so this is log Y. And say alpha is equal to log A. Okay, so beta is equal to B. Okay, and then capital X is equal to log small x. Okay, can you see this? Now what we have? We have Y equal to alpha, okay, plus beta multiply capital X. So this is a linear model, correct? Okay, so the point is now if you have this kind of model, okay, you take transformation both side log x, okay, and log y, then you will have alpha is log A, beta is B. Okay, this is the final result. Okay, so let's practice this. Okay, let's practice this with this kind of data. So say this is the data that you have. Okay, so let's go to open Excel. Yeah, can you see the Excel here? Okay. You can also open your own. Okay, so then we put X and Y. Okay, and then we type the data here. Yeah, 7, 14, 24, 30, 45, and 57. Is that correct? Next, we have 24, 34, 45, 50, 61, and 69. Okay, so this is the data that we have. Okay. Okay. They type your own in. Okay, so what we will do, so let's start to plot this. Okay, so you go to XY. Yeah, so there. So if you plot this, it's not really straight line. Yeah. And if you just use the trend line, like this. There. Yeah. So if you use power there, okay, you use power and then you display the equation on chart, okay, you will get quite good. Yeah. What happens if you use other model logarithm? This is 97%. Okay. Linear is 897, exponential 92, and power is the highest, 99. Okay. So, but how are we going to use, okay, without this trend line? Okay. Can we compute this manually? Okay. Uh, why we want to compute manually if there is already a trend line? Because if you know how to compute this manually, for one particular model, for example, the power model, which already have that, then you know how to use the same method for other model. Okay, so okay, let's do it this manually. Yeah, so I have remember the formula a while ago. Yeah, this is the one that we will transform. Yeah, so we transform by having log y and then we will have log x. And so in that case, just log x and we have log y. Okay, so you can use any basis of the log, yeah? As long as the same basis, that's okay. So say I can just put log. So for example, you can just log or you just use log 10. That's okay. Awesome. Yeah. So say I have log of x. Yeah. Now the base, if you don't put, yeah, it will be the default of Excel. Yeah. So say for example, I put base 2. Yeah. It's up to you to put whatever base that you want. Yeah. So in here, I will just arbitrarily put base 2. Yeah. Okay. So then I copy this to all. Okay. And then now if you plot this, yeah, log x and log y, okay, there. This will become exactly linear. Okay. You will see this if you add the trend line here, okay, and put the, yeah, you will get exactly linear, yeah, which have the same r square. Yeah, you have exactly the same r square. But the value, okay, is now 0.5 and then plus 3.17. Yeah. This is the slope and the intercept of this one. Okay. So then we can calculate the slope, okay, and the intercept. Okay. What we use is not the slope and intercept of the original data. Okay. So we use the slope of intercept of the transform data, which is log x and log y. Okay. So there. So you say slope, there's the slope. Okay. Slope have known y and then known x. So in this case, you use known y and then known x with this. Okay. Same thing with intercept. So you use intercept there. Yeah, the same. Known y and then known x. So use this one, known y and then known x. Okay. So You will see here, this is 0.9529. This is exactly here also in the drawing. Yeah. Okay. The same thing, the intercept 3.1753. Yeah. And this is 527. This is exactly the same, yeah. Just different in rounding off. Right? Okay, until here you can follow. Okay. So yeah, I'm in the slide I'm use different base of the logarithm. Yeah. So in here I use 10. Okay. But in the example of Excel here I use 2. Okay. That's why the numbers are not the same. But how can the number not the same? Can we get actually the correct result? Yes, you can. Yeah. You can get the correct result because basically the base does not matter. Yeah. So as long as you use the same base. So what is the actual result? The actual result, you're supposed to get alpha and beta. So if you look at this, log A is alpha. Yeah, log A equal alpha, right? So what is this log A in our Excel? This is the intercept, right? So this is the log A, okay? And then B is beta, okay? So this is B, yeah? And this is the alpha, okay? And then this is beta, okay? Then, oh, we already have the alpha and beta, but what we want is not alpha and beta because our original model is A and B, it's not alpha and beta, isn't it? So how to get the A and B? Oh, B is already the same as beta, so this is will not change. But log A is equal to alpha. This is alpha, yeah, 3.17 is alpha. How about A? How do you get A? If log A is equal alpha, this one, okay. So if we know alpha is equal log A, what is A? Anyone knows? If log A equal alpha, we already know log A is equal to the intercept, which is 3.1752, right? But I don't want alpha, I want A. So this is where the base matter, okay? So A is equal to the base exponent alpha, okay? So A is equal to base, okay, exponent alpha, okay? So in this case, remember we use base 2 here. So then A is equal to 2 exponent alpha, this one. And we have 9.03. Yeah. So if you look at the, oh, where is that? Sorry. Oh, can you see in the slide? Exact the same, yeah. Okay. So we have exactly the same. Even though we use the different values. Mhm. see this? Even though we use different base value, okay, here we use 2 and here we use 10, okay, we get exactly the same, yeah, 9.03, yeah, 9.03, okay, and then the slope of beta is the same also, yeah, 0.5, right? So this is the result, yeah. This is the actual result, so I will put orange here. This is the actual result. So what is our model a while ago? This one, yeah. Y equal to A times X exponent B, yeah. So our model is actually Y equal A multiplied by X exponent B. Oh, we already know A and B. That is the same as A is 9.03334, okay, multiplied by any X, okay, X is the data, right? Exponent, oh, sorry, exponent. Exponent, what is this? P is 0.5029, yeah. Okay, so if you already know the model, okay, with the parameter, so this is calibrated parameter, right? Then you can predict, okay? So I have new X here, okay? I want to predict what is the value. Oh, say I have a new X, what number you want? 10, okay, and then 12. Okay, let's try 14, which is already in the data. Okay, this is what we want to predict, yeah? So predict the value of Y. How do you predict this? Anyone knows?
Substitute po, sir. Substitute the value of x to the equation, sir.
Yes, so we have the equation, yeah, this one, right? Okay, so what we have is okay, before that, so let's put the same, the name, so that we can substitute easily, okay? So this is, the name is P, okay? I put underscore because Excel does not allow one letter. Okay? And then let's name this A here, A underscore, okay? So then what we have, so we have A, oh, yeah, multiply by this X, okay? Exponent of P, okay? So that is the result. Yeah, this is the predicted value. Then you can just copy this down. Yeah, there. Okay, if you look at this, 14 was 34. In here is not exactly 34, 34.06. There is some difference. Yeah, that difference is called error, right? So small error is allowed. Is this clear or not? Okay, so if this is clear, you can do the same for other model, yeah? So you can do the same for other model. Let's use the same data. Okay, so this is the data that you already typed. Okay, what happens if we use different model with this logarithmic curve? Ah, okay, so this is also allowed, exists in Excel, yeah? Logarithmic curve is already exists. So this is the model. Y is equal to ln of A times exponent B. Oh, this is different value. Now, if you look at this, okay, we can transform this model, okay, into, okay, linear model. Okay, how? So we only take the ln in one side, not two sides. Okay, so this is already ln of a x exponent b. So in this case, we can expand this part, right? The right-hand side, we can expand. So this is the same as ln a plus b ln x. Oh, so ln a, alpha, b, beta, and then capital X here become ln x. Okay, so in this case, we have a new model which is linear. Okay, and you can try. Okay, okay, I will demonstrate with you. Okay, this is the same data. Okay, and we use this. So I just copy down here. Okay, right. So our model now different. Okay, so our model is this one now. Okay, we use this model. So what happened if we use this model? How are we going to get the slope and intercept? Anyone knows? Okay, we still compute the slope and intercept, but what's the difference with the power above? Okay, in the power above, when we use slope and intercept, we use log x and log y. Okay, but in here we don't do that. Okay, so now depending on the model transformation here, if you look at this, just copy this and put here. Okay, so if you look at the model transformation here, okay, only the ln x, yeah, the y still remain y. Yeah, can you see this? The transformation. Only the in the x is ln x, but the y is not log y. Yeah, so still the same y. Okay, so in that case we use slope. Okay, we use y here, and then the x is not x, but we use log x. Is it clear or not? That's the difference. Yeah, depending on the different transformation. So this is how you will use. Okay, so the same thing now. Intercept. You just use intercept. Okay, so the y is now this y. Okay, it's not log y. Yeah, it's this original y. And then the x now become log x. There. So this slope is beta, right? Which is the same as b. This intercept is alpha. Okay. But this is the same as ln a. Oh, what we want is not alpha beta. What we want is a and b. So how do you get a? Do you remember? A depends on the base of the logarithm. Yeah. So if your logarithm is base 2, then you will use 2 exponent alpha. Yeah. So A equal to the base, which is 2 exponent alpha. There. This is almost 0. Yeah. So, oops, where is this? Yeah, this is very, very small. Yeah. Is this clear or not? Yeah, this is the result will be similar. Yeah. So next one, okay. How about if our model is actually square root like this? Huh? Okay, so if your model is square root, okay, again you can transform the y still the same as y, but the x now becomes square root of x. So in that case, you create square root here, and then you get the slope from y and the square root of x. Okay. In this case, alpha is equal to A, beta is equal to B. So this is easy. Yeah. Square root is not available in Excel. So you need to make it on your own. Okay. Can you follow this, or you have any question, or is it not unclear? Yeah. The same thing. Okay. If your model is harmonic, something like this, yeah, y equal to 1 over a plus bx. Yeah. So then again, it is you need to transform into linear model. So how do you transform? Okay. So you take reciprocal for both sides. So this small y with accent is 1 over y. X is actually the same x. Okay. Then you will get this result, yeah, model after transformation. So depending on the transformation that you have, okay, now you can get the slope and the intercept. Yeah, this in this case exactly the same. Yeah, alpha is equal to A, beta is equal to B after you transform. Right. Again, this model is not available in Excel. Okay, so you can do it on your own. Yeah. Okay, you can also make it more complicated model. Okay, y equal to A plus B divided by. Yeah. Again, this is the transformation, and this is the model after the transformation. Yeah. This one is square harmonic. Okay. So 1 over A plus BX x squared. Yeah. Again, now you can create your own nonlinear model if you can transform that into uh, a linear model. Okay. Then you will have your own model. So the R square is still the same, okay? The way to do the t-test and so on is still the same. Okay? The only difference is this non-linear model, you transform them into linear model. Okay? So any question? Yeah. Yes, Justin.
Sir, like to clarify only,
Yes.
um, will the transformed linear model always follow the format of a plus bx?
Yes.
I mean the slope format, yeah.
Yes.
Okay.
But
Thank you, sir.
you can reverse it, no? You can have like this, huh? Y equal mx plus c. That's same.
Okay.
Yeah. So
Thank you, sir.
yeah, thank you. So the same linear model transformation a while ago, now we can generalize into matrix form. Okay. This is what we use in real life. Okay. The one that I show here is very simple. It's only one x and one y. Okay. But in real life, you will have many uh, variables, not just one. Right? But let's start with the simplest one. It's only the same thing, yeah? Y equal mx plus c. Yeah? Simple linear regression. Okay. Say you have this y equal mx plus c or b times x plus a while ago, right? Okay. So what happens if you have this? Yeah. So we list the model for each data. Yeah. So your data is x1, y1, x2, y2, and so on until xn, yn. Yeah. This is the model is linear. So you have the slope m, c is the intercept, right? So and then we list down like this. Yeah. But if you look at this kind of listing down each row in the model, this is exactly the same, right? M, and here is also exactly the same, C. Okay, so we can put this into matrix form, yeah? So how do you put this into matrix form? Look at exactly the same here. So the right hand side is y, so I put it like this, y, yeah, y1 until yn, okay? And then I will follow this format exactly, you see, yeah? So this is m times x, yeah? So in this case, I will put the x, okay? This one is c times 1, right? The intercept should have certain value. So in this case, I just put 1 here. Okay, so if you look at this, I hope you remember matrix multiplication. Okay, so this row multiplied by that column equal to this value. So here, x1 multiplied by m plus 1 multiplied by c equal to y. Oh, exactly this value. Yeah. So in the second row, you have x2 multiplied by m plus 1 multiplied by c equal to the second value, which is y2. So exactly this row. Is this clear? Okay. So my question, if you have the data, can you put into matrix form like this? Yeah. The next question is not just how, but why. Why do you want to put it into matrix form? Yeah. As long as your model is linear, if you put it into matrix form, okay, suddenly everything becomes simple. Okay, you can solve it easily using generalized inverse. Okay, I will show you in a moment. Yeah, so if you put this into matrix form, this is the x and this is 1, right? So x and 1. Then I will name this matrix A. Okay, and this the second one here, M and C, I will name it as vector B, and this is vector Y. Okay, so can you see? I just rename this, and suddenly we have very simple model A times B equal Y. Okay, and this is the general, very general model, even though this is very simple. Yeah, which is just A times B equal Y. That's it. Okay. But you see, we can solve this using linear or nonlinear, exactly the same equation. Okay. Okay, I will show you in a moment. Let's go to the solution. Okay, later. I will show you how to get this into your data into this matrix form first. Is that okay? So I will skip this part first. Okay. So this is the example of your linear regression last week. Yeah, you have the year and population, right? So what you will do, okay? You will have X here, the year. I will put this in the here in the Excel, and then I will put 1 here. Okay, and then the population, the Y, still remain like this. Okay. Okay. Now, what happens if I have this data, the one in yellow here? Huh? This is the data for second-hand car for the same type of car, for example, Toyota. Right? So this is the age in month. This is the kilometer of the vehicles. This is 10 vehicles survey. Yeah, used car, this one. Okay, and this is in pesos, the price. Okay, so in here you look at this. This is no longer one variable. I have two variables, x, yeah, which is the month and the kilometer. Yeah, I can put this exactly the same into a b equal y. Yeah, how? Look at this model that I have. I have a plus b times h plus c times kilometer. Okay, what I will do, I will put that into matrix, because we have a here, okay, a times 1, right? And because there is no variable, so a is times 1, so I will put here a times 1, 1, 1, 1, 1, 1, okay? And this one is the data, and this is the age, this is the kilometer, and this is the price. Is it clear? So now I have a times b equal y. Okay, different data, but as long as I can put it into A and B, I can solve it. Nice. Okay, again, another example. So once you have this, okay, you can solve this one. Yeah. Later I will show you how to compute this. Okay, and how to predict. Okay, let's see another example. If you have multiple linear regression like this, okay, again you can solve it using A, B equal 1. Yeah. In fact, you can even use this the same for nonlinear. Yeah, for example, polynomial. Yeah. So as long as you have the variables, you can put it into the same matrix. Yeah. A times B. Yeah. For example, polynomial regression like this. Yeah. So this is the same. Yeah. So you have x squared until xp. So you can put all of this x into the matrix A, and this parameter here become the vector. Yeah, the last one is 1, right? Then you can get you can solve this using generalized inverse later. Is this clear or not? This is very powerful. Okay, very simple but very powerful. Why? Because using one technique, you can solve many model, including nonlinear. Okay. The equation is only a times b equal y. Very simple. Okay. Okay. Now, how to solve this one? Okay. How to solve this one? So if you have this a times b equal y, okay, how to solve this one? Okay. We, uh, 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 we remember the matrix A here is not square matrix. If it is square matrix, you have inverse, right? But your matrix is not square, so you need to get what is called generalized inverse. Okay? Generalized inverse is just like inverse, but okay, this is for rectangular matrix, not square matrix. Yeah. Of course, if it is square matrix, it becomes just normal inverse. Okay. So it is more general than the usual inverse. Okay. So the trick is to multiply the matrix A, okay, with its transpose. Okay. So do you want me to show? Okay. Let's show this in Notepad. Okay, let's show this in Notepad so that you can see. So I have A times B equal Y. Okay, so if I have A times B equal Y, okay, now I need to get, remember A is not square matrix, it's a rectangular. Okay, so to make matrix in a rectangular matrix into square, you multiply by its transpose. Okay, so that's the technique. Yeah. So in this case, I will multiply by the transpose. So let's call this A accent as the transpose. Okay, multiply by A times B. Oh, in the left-hand side, you multiply by the transpose. Then to make it equal, then okay, you on the right-hand side, you must okay, multiply with the same thing. Okay, so there. This is clear or not? Okay, remember in the equation, the most important sign is the equal. Okay, that means if you multiply on the right side, left side here with A accent, with A transpose, then the right side must also should that equal, you need to multiply with the same thing. Yeah. Okay. So next, this is already this part is already a square matrix. Okay. So let's put this okay with the parenthesis. Yeah. Because this is a square matrix. Okay. Does not change, right? I just put parenthesis, it does not change, so it's okay. So let's copy this down here. Okay. So now, because this is already a square matrix, remember, yeah, any rectangular matrix multiplied by its transpose, either from the left or the right, it will become square matrix. Now, because this is already square matrix, what you can do, you can inverse it. So, okay, I multiply, okay, this one with its inverse. Okay, so I copy here, multiply with its inverse. Yeah? So this one is exponent minus 1. Minus 1. This is meaning this is an inverse. Okay? But the left-hand side multiply by inverse. So if the left is multiplied with one thing, so the equal, you need to multiply the same thing. Isn't it? Okay, otherwise it will not become equal. So you need to multiply with the same thing so that become equal. So I put here the equal there. Equal is the most important sign. So to make it balance, okay, you need to multiply with the same thing. Oh, yeah, this is in slide. Can you see this? This is the result, right? Okay. So, but remember, a matrix multiplied by its inverse is identity matrix. Okay. So, collapse become identity matrix times B. It is the same as this one. Okay. So, yeah. Is it clear? But identity matrix is just one. No? One multiplied by anything is that anything, right? So this is exactly the same as P. Okay. Yeah, I get the solution. P equal. This is what we want, right? The P is the parameter, isn't it? Oh, there, we get this. Look like very complex, but this is actually simple, yeah? Yeah. You just remember this A transpose times A inverse times A transpose. Ah, then we call this, let's call this L, yeah, because this is left generalized inverse, yeah. There's also another one is right generalized inverse. Okay, so this, I just put this A transpose times A inverse times A transpose now become new matrix. Let's call this L. Oh, I got the left generalized inverse. Then how to get the P? Just L times Y. Wow, simple. Yeah. And you can solve this in Excel. Okay. Later when you want to solve IFN, you will use exactly the same method. Yeah. That's why I need to introduce this early. Okay. Okay. So once you have this, let's solve our problem. Okay. Of this one. So how are we going to do? Okay, this is our problem last week, right? You still have your Excel, you have it, so you can make A, okay? And then what you will do, our goal is to create L, left generalized left inverse, right? Which is inverse of A transpose times A multiplied by A transpose. Okay, so in that case, I have A, then I transpose first. Yeah, in Excel, you just use equal transpose. Okay, and then what you will do, A multiplied by, oh no, A transpose multiplied by A. Yeah, okay, here, A transpose multiplied by A. And then what you will do, you inverse this one. Yeah, this is the inverse, right? And then what you will do, multiply this inverse with A transpose. Then you get L. Okay, then what you will do, multiply this with Y, you will get B. Get the result. Okay, let's practice together. Is that okay? In Excel. Okay. Okay, I will create a new sheet. Okay, I will type the data. Okay, 1980. Okay, this one is equal above plus 5, right? Okay, so we don't have this. No problem. So this is the year, and this one is the population, yeah. So 2.1, 2.9, 3.2, 4.1, and 4.9. Okay. Okay. You can try. So then what we will do, we will form a matrix A. Okay. Matrix A consists of X and 1. Okay. So A is equal to X and 1. Oh, there. I just copy the X. Okay. I copy here. And then this is just 1. 1. Just type 1 and then copy. Okay. This one is A. Let's color it the same. There. Okay. Let's name this A. Yeah? So I will, so that easily to show, I'll put M A. Okay. There. So let's name this matrix A or MA. Can you see? Okay, you go to name box and then keep the name. Okay? So next, I want to get A transpose. All right? How to get A transpose? Equal transpose there. Okay? Which is of MA. There, you get that. Is this too fast? No? Okay. So you type there. Oh, the result is value. No problem. Okay. Remember, what is the size of this matrix? Remember, when you deal with matrix, you need to know the size. Okay. The size is 1, 2, 3, 4, 5. So the size is 5 times 2. Right? This is the size. Okay. So in this case, the size of this is transpose. So 2 times 5. And the size is 2 times 5. Remember, if you don't know the size, you cannot solve. Yeah, you need to solve, you need to know the size. Okay, so transpose is just reverse, right? It's from vertical become horizontal, from horizontal become vertical. Yeah. So here I have 2 times 5. So I need to go 1, 2, 3, 4, 5. Yeah, you highlight like that. Okay, after you put the equation, okay, in the left top corner, okay, then you highlight this. Is this clear or not? Okay, and then you click here in the formula bar. There. Okay, and then what you will do, okay, you press Shift, Control, Enter together. Yeah, Shift, Control, and then Enter. Oh, oops. What happened? Shift, Control, and okay. Maybe this is incorrect. Why this is incorrect? My finger is not correctly put Shift, Control, and Enter. Okay. How do you know that this is incorrect? If this is correct, it will become array. Yeah. So if it is incorrect, no array. So I come back again here. Okay. Shift, Control, Enter. No, this is correct. Yeah. If you put it correct, you will see this is an array. Can you see there is a bracket there? Good. Can you get this exactly the same? Okay. Once you have this, okay, I will color this. Okay, I will color this, and I will give name. Okay, what's the name? A transpose AT. Yeah. Okay. So A transpose. Okay. Can you do that? Yeah, remember, yeah, the command is control, okay, plus shift plus enter, yeah, together. Okay. Oh, practice first. Usually this is the difficult part for you who does not familiar with Excel array. Okay, so once you know this, everything is simple. Am I too fast? Is that? Okay. Any question? So the next step is to get the A transpose times A, isn't it? Because our goal is to get the generalized left inverse, yeah? So I calculate here A transpose, okay, times A, okay? So that's multiply, right? So that's equal to M, no. You want to get multiply. Oh, there, M volt. Yeah, M volt is matrix multiplication. Okay, there, I just stop. What do you want to multiply? A transpose, AT, times A. Oh, if this is correct, okay, you will see Excel immediately type the name. Can you see this? Okay, if not correct, so you will not get that name. Yeah, the name that you already set in the name box. So I will close this. Okay. But this is only one number. Okay. A transpose is 2 times 5. A is 5 times 2. Okay, so matrix multiplication, okay, you have 2 times 5 multiplied with 5 times 2, okay, you will get 2 times 2. Yeah. If you want to do matrix multiplication, okay, this is the rule. Yeah. If you have the number of row, okay, here, and then multiply by the number of row 2. Sorry, this is so the number of row is 2, right? The number of column is 5, okay, and then you can only multiply if the number of column in the first matrix is equal to the number of row in the second matrix. In here, 5 and 5. Okay. Matrix multiplication is not commutative. You cannot reverse. Okay. That's why the size matter. Okay. Here, the number of column is 5. And then in the first matrix, in the second matrix, the number of row is 5. So that's why you can multiply. And then the result will be the number of row in the first matrix and the number of columns in the second matrix. Okay, I'll give you an example here. What happens if I have 3 times 5 multiply by 6 times 4. What is the new size? Can we multiply? Cannot, because 5 is not equal to 6. So you cannot multiply. Okay? So you can only multiply if this one, okay, is the same as, yeah, the column of the first matrix is equal to the row of the second matrix. So if you put 6 in here, can we multiply? Yes, because 6 is equal to 6 here. Yeah. So what is the result? Okay, the result is 3 times 4. Yes, Romeo?
No, sir. I thought you were asking what is
Oh,
the
okay,
result.
okay, okay. Okay. So the result is 3 times 4. Okay. Yeah, very good. Yeah. Okay. 3 times 4. Okay. Now, come back here. What is the result of this size? A transpose times A. Yes, Romeo.
2 by 2.
Very good. So knowing the size is important, yeah, because that is how you highlight. Okay. So again, you highlight 2 by 2. Can you see this? 2 by 2. And then what you will do, you go to this formula bar, click like this. Okay. And then what you will do, Shift, Control, Enter together. Yeah. Shift and Control, and then Enter. There you get the result. Yeah, as if by magic. Yeah. There. Now, to get the generalized left inverse, I need to inverse this matrix, isn't it? So I need to inverse this matrix. Okay. Because this is already square matrix. Okay, I need to get the inverse of this. Yeah, inverse of this one. How do you get the inverse? Oh, Excel already have the function. Yeah. So M inverse. There, M inverse of this one, right? So I just close this. Yeah. What is the size? Inverse is the same size as the original matrix. Yeah. So this is 2 by 2, right? So then the size is also 2 by 2. Okay. So we need to know the size so that you can highlight. Okay. Without that, you will not get the correct result. Right? So once you highlight that, what you will do, you click here and then Shift, Control, Enter. Clear? Yes, Romeo, you want to ask question?
Sir, even if I'm not pressing on the shift control enter, the answer already
Oh,
appears.
good. Yeah, the new Excel probably. This is my Excel is very old, 2016. The new one is already automatic. Yeah,
Okay, sir. Thank you.
that's better. Okay. So you get this. Huh? Then what you will get, the next step is to get the generalized left inverse. Yeah. L, okay, is equal to this one. Okay. L is equal to this one, the inverse, multiplied by the A transpose, yeah? A transpose. Okay, so, oh, the size matter now. This one is 2 by 2, right? And then this is 2 by 5. Can we multiply? Yes, yeah? because 2 is the same as 2, but the result is 2 by 5, yeah? So the result must be 2 by 5. So I will multiply, right? M mul this one, the inverse, and the transpose. Okay. Okay. And then what I will do, I get the size 1, 2, 3, 4, 5, 1, 2. Okay. And then click Shift Control Enter. Yay! I got the generalized left inverse L underscore. Okay, so if I already get the generalized left inverse, that's easy. I can get the so the y is this one, yeah, the population, isn't it? Okay, so what you want to get is the vector b, yeah, which is the same as the slope, okay, and the intercept, isn't it? Okay, this is the slope and the intercept. B is equal to what? L times y. Yeah? The y is the population. Yeah. So that multiply mean matrix multiplication. Okay. So then I will do M mul of this generalized left inverse. Okay. And then this theta. Yeah. This is the y. Okay. Then again, the size is, what is the size? This is 2 by 5 multiplied by 5 by 1. Okay, so this one, the size is 2 by 1. Right? So in that case, I just put like this, 2 by 1. Okay. Shift, Control, Enter. There. I get exactly the same result. Yeah, this is the final result. Yeah. So this is how you calibrate your data using regression. Okay. Is this clear or not? Okay, so I'll give you uh, time to practice, okay, this one. Can you? Can you just type this data? Yeah, I'm only 10 by 3. Okay, and then you do the same, yeah. You create the matrix A and B, vector B, and then you do exactly like this, yeah. Okay, now you get the left generalized inverse, and then you get the B. Can you do that? Okay, try. So once you finish, okay, 2 or 3 person can show, okay, and you can claim it as your recitation, yeah. Don't forget to claim your recitation later, yeah, in a model in Referral 2, yeah. So when you claim recitation, please, I recite practice 3 in this slide like that, yeah. Okay, so this is the data. Go ahead. Yes, Lian.
I already got the B, sir.
Oh, good. You want to share?
Can you see my screen?
Yes, you can see your screen. Very good.
Yep. So
Can
I
I see the
just
result? Can I see the result? Oh, very good. Okay, excellent. Yes. Excellent. So, can you predict now? Go to the next slide. Once you have done the calibration, okay, can you predict uh, if I have a second-hand car, new, okay, 21 month, and then it has been driven for 14,991 kilometer. Can you estimate the price? Yeah. So, can you estimate the price if I have, okay, another car which is not there? Yeah, 21 month, and then it has been driven by for almost 15,000 kilometers. Yeah. Yes, Justin, you want to share your screen?
Yes, sir.
Okay, go ahead.
Is it available now, sir? Can you see?
Yes, I can see. Yes, very
Uh,
good.
Here, sir. I actually just,
Oh, you can estimate also. Super.
yeah,
Yes.
because I included the whole decimals of the
No
other.
problem, no problem. Yeah. So super. So you know the price is now about 600,000 pesos. Yeah.
Yes, sir.
Super. So you can predict using this. Okay. So you can start a new business of selling car. Okay. Okay. So important is once you have the model, you get the data, okay, and then you create a model, then you can predict. And aside from prediction, you can also control. So what's the meaning of control? If I want to get, yeah, if I want to make, say I have only 300,000 pesos, okay, and I want almost new car, say within 1 year, so 12 months. Okay, how many kilometer? So control mean you have the output, the price in this case, okay, and I want to get one of the input. Okay. Okay. So yes, there is a call seek in Excel. You can use that. You know, in what if analysis data, what if analysis, and then call seek. Then you can use to control. Okay, try. So everyone get the result already. Is it difficult? So tell me uh, how's your level of difficulty in this case? Is this easy or difficult, or am I too fast for you, or this is just okay? Yes, good. So once you get this estimation, this is calibrating, right? Okay, understanding with calibrating. Okay, so now we can start to interpret. Yeah, once you have the model, now you start to interpret. Okay, what is the interpretation here? First, we verify. Okay, verification, right? You have calibration, you have validation, we did not discuss, but we need to have verification. The model, if you look at the model, okay, if you look at the model here, okay, this is the model, right? Price equal to A times something. This is the model. Okay. What happens if the age is 0 and then the kilometer is 0? When the age is 0 and kilometer is 0, then price equal A. What is your A a while ago? 900,000. Oh, that is, what is the meaning of age 0 and kilometer 0? New car, isn't it? Huh? So that means A is the price of a new car. So the parameter you start to interpret, okay, by putting the values here, yeah. Okay, for example, 0 and 0, then you know, oh, A is the price of new car. And that in that case, what is B? And what is C? What's the meaning? Anyone know? Yes, Romeo? B is, oh, you are mute.
Number of months and the distance.
Uh,
B is the number of months, C is the distance.
no,
Or
it's a slope. It's a change. Okay, yes, Ken?
B basically is the rate of deterioration of the price based on age, and C is the B is the rate of the deterioration of the price based on the age, and then C is the rate of deterioration of the price based on the kilometrage.
Exactly. Okay, excellent, Ken. Yeah. So the rate means the slope. Yeah, the change. Okay. So and Ken mentioned this is deterioration. That means this must be negative, right? Okay. So check your result. Is it negative? Yes. So if this is not negative, okay, after you get the data, you calibrate it. If this is not negative, something is wrong with your data or your way to calibrate, isn't it? Okay. So always verify, okay, once you get the model, verify based on the meaning, okay, and the range. Clear, yeah? So, okay, I got the meaning of A, B, and C. Very good. So then I can predict, right? So I have the months and the kilometer I can estimate, yeah? So around 600,000, okay? Now, okay, the next step is to do what is called dimensional analysis, huh? This is very important. Why? Because using dimensional analysis, okay, you can also check the range of the value and the sign of the parameter. Yeah. So, what is the meaning of dimensional analysis? You need to check the dimension, the unit. Okay. Every time you do an equation, don't forget, okay, check the unit, yeah, the dimension. Okay. This is the model is called multiple linear regression like this. Yeah. So h is basically x1, kilometer is x2, isn't it? Okay. So then you check, yeah. So the price is, for example, in pesos or US dollar. Okay. A, we don't know. B, we don't know. H is in month. Okay. C multiplied by mileage. Mileage is in kilometer, right? So, and then you set the two of them 0, right? H and mileage is 0, then you get A. So in that case, the dimension of A, the unit of A is the same, yeah, the same as the price. Okay, so if this is pesos, it's pesos, this is dollar in dollar. Okay, and now we have the A. How about B? Yeah, then when you put the x2, the mileage is 0. Okay, now you have A is in price, in dollar already. Now, what is the dimension of P, the unit? Yes, Romeo? You are in mute.
Sir, I think while B and C are both negative since it reduces the price.
Hmm.
The unit of B is equal to peso per month.
Yes. And C is in peso per kilometer.
Peso per kilometer.
Yes. And then you check this one, yeah? This is the very important dimensional analysis check. Okay? Okay. The unit on the left-hand side must be exactly the same as right-hand side. Okay? So, yeah, gradient, the slope, margin, rate. Yeah, these are the different jargon, different terminology, basically the same meaning. Okay, so we do how about the sign? The sign is clear also, yeah, based on the meaning. So the sign of A must be positive because that is the price of new car. The sign of B and C must be negative, yeah. Now, how to get the actual range? You need to assume. In modeling, you need to dare to assume, yeah. So let's assume that because this is used car, I will just take after 15 years, no value. Okay. You don't like 15, you can put any number that you like. Say 12 years, 20 years is okay. Yeah. So I have no more value after 15 years. So that 15 means 180 months. Or after 5 kilometer of 5 million kilometers. This is very extreme. Yeah. So based on these extreme values, okay, then you can estimate the value, the range, yeah, the range of B and C. Yeah. How about the price of the A? The A, you just visit the dealer, isn't it? Okay. So, and the value of B depends on A. The same thing, yeah, the value of C depends on A. Okay. So you get the range of the value. So what's the meaning? If the range of the value, if the value of P and the value of C beyond that range, that means something is wrong, isn't it? So why you need this kind of thinking? Because you need to verify, okay? You need to verify whether your parameter that you just calibrated is correct or not, logic or not. Okay, always like that. Yeah, dimensional analysis, verify the logic, okay, based on the range. If this is going beyond that range, practically the model cannot be used. Okay? Is this useful for you? Right? Next. This is come from the book of our reference, Ortuzar and Willumsen. Yeah? This table. Check the T value, T statistic, and the sign. Yeah? Remember the T statistic must be larger than 1.645 for 10% error, 1.96. Yeah, this is based on normal distribution. Okay, for 5% error. Yeah, so that's called significant or not. Yeah, so if the T value, this one, okay, and this is the sign, right? So check the sign and the T value, and then check also this variable is policy variable or other variable. Policy variable means the things that you can control. Remember, policy variable means the variable that you can control. As a planner, you want to control, right? What are example of policy variable? Cost, yeah? Time, okay? Maybe the price, okay? Something that you can control. Okay? That is the one that called policy variable. Now, if the sign of that variable is correct and significant, of course, you include, right? Okay. Now, if the sign is correct, but the t-test is not significant, nah, this is the suggestion. You need, if this is policy variable, you still include anyway. Can you see this? Even though the t-test is not significant, yeah, you still include, yeah. But if this is other variable, not policy, you just reject that. So exclude from the model. Okay? But if it is a wrong sign, then you have a problem. Okay, so the sign is more important than the t-test, yeah. So especially if you have a wrong sign and the t-test is significant, you have very big problem. Okay. Okay. If this is just other variable, not policy variable, you just reject. That's okay, right? But if this is policy variable, you have headache here. Okay. Again, modeling is an art, so you need to check. Maybe your model is not linear. Maybe you need to use different model. Maybe you need to use ratio, you multiply. Okay, not just linear model. I don't know. So there are many models that you will try. That's why we discuss about many different models, because you will try one by one, right? Which one is the best? Now we don't know. Okay. You understand? Okay. Now I give you the tips how to select. Okay, how to select variables or how to select model. Yeah. So the tips, we use multiple linear regression, something like this example a while ago. Yeah, the car estimation. Okay, so let's do this. Now, say you have this data. Okay, I have n variable of the x. Yeah, of course the output is only one, y. Okay, then what you will do? Because there are n variable, you have a lot of combination of this model. Okay, you need to select the best model, isn't it? Okay, you don't just use R square, you know. Okay? If you just use R square to select model, you can get wrong. Why? Because if they are highly correlated, the R square must be very high, always. But that's cheating. Okay? By cheating, mean you get overfit. That means you cannot use this for prediction. Okay? So test the correlation. Number one is you list down the combination of all the model, and then you check the correlation, yeah, between X. Okay. So, and no high correlation between X. Okay. So, and then of course you need to test using t-value, f, r square, yeah, and then the best model is the highest r square that you don't reject. So take the feasibility of the combination first. Okay, I'll give you an example. Okay, here. Say I have 4 variables, x1, x2, x3, x4. Okay, then I computed the correlation matrix. These are the example of correlation matrix that I have. Okay, so correlation matrix is symmetric. So the upper part here is exactly the same as the lower part. Okay, so see the upper part, right? The upper triangle is the same as the lower triangle. Okay, so check the high correlation. Yeah, high correlation means above 0.9. Okay, or we have 2. Yeah, this one and this one, isn't it? Huh? So if Between X and Y, between the independent and dependent, we need to use high correlation. Okay. Between X cannot have high correlation. Can you get it? So this one, X and Y. Oh, the correlation is very low, right? In that case, this one, no more. We don't use this because the correlation is low between input and output. Okay, if only one variable. If they are high correlation, you use. Okay, if low, you don't use. But between input must not have high correlation. Okay, so these are the list of combination of model, isn't it? So I have 4. Now we can use 1 variable, 2 variable, 3 variable, and 4 variables. So yeah, x1, x2, x1, x3, x2, x3, x2, x4, x3, x4. So these are combination. So you list down all the combination possible, all possible model. Okay. So then what we will do? This is less than 0.6, so we don't use. Yeah. How about this one? This one also, yeah. X1 and X3, high correlation, isn't it? So we don't use. This one is we don't use. Yeah. The same thing, everything that contain high correlation with this X2 and X4, we exclude. Yeah. This one, X1 and X3, so we don't use. Yeah. This one is X2 and X4, we don't use. Yeah. This one is X1, X3. Yeah. This one is X2, X4. This one is X2, X4, and X1, X3. So this is not used. Finally, you have only 3 models to be feasible. Yeah? This is the feasible model that you will consider later. So among these 3, then you check the t-test, the f-test, and the r-square. Is this clear? The steps? Any question? So with this, we finished the first part of our slide. Okay, so if you have any question, go ahead. Charts. So, yes, Justin, you want to ask?
It's not actually about that lesson, sir, but I was wondering if we could get a copy of the recordings of the classes so we can review
Oh,
them.
I always put the recording of the class and then put there in Moodle. Can you see?
Okay.
This is
I'll
2 weeks
check.
ago. This is last week. Okay? I always put there, including the AI summary. Can you
I'll
see?
just look into it, sir. Okay, thank you.
Yes. Please check your Moodle. Okay? Right after the class, I always put there. Okay? Good. So let's go to the next topic in that case, which is traffic flow model. Okay, go to Moodle. I think you have the traffic flow model. Yeah, traffic flow theory. Yeah, and then you will have an assignment. Is that correct? This one, yeah. The assignment is green shield, supposed to be for next week. Correct, for next week. Yeah. Okay. Okay, let's start. So the slide here I put mainly for pedestrian, but you can also apply this for vehicles. Yeah. So this is called traffic flow theory. Okay. Now, in traffic flow, you have two big way to get the performance. Okay? So one is called macroscopic. Okay, the other one is called microscopic. Yeah, macroscopic mean aggregate level. You get in the overview. Okay, while in the macroscopic you go down into individual level. Okay, so these are example of macroscopic traffic flow performance. Yeah, flow rate. Sometimes we call it volume. Okay, or speed. Yeah, density, area module, queue length, yeah, waiting time. These are macroscopic level. Okay, and then we also have what is called microscopic level. Yeah, headway. Headway is the time between two cars. Yeah, or pedestrians. Yeah, and then spacing. Headway is the time, spacing is the space between two consecutive vehicles. Yeah? And instead of the actual average speed in here, you have what is called instant speed of the individual vehicles or person, yeah, or pedestrian. Yeah? The same thing, you have instant delay or uncomfortability index of the individual. Yeah? These are example of traffic flow performance, yeah, based on either macroscopic or microscopic level. Yeah. So the most important is this three.
Sir,
Yes.
sir, can you show us the slide?
Oh, I did not show you the slide. Yeah.
Thank you, sir.
Thank you. Sorry. Okay. Can you see? Okay. So the most important is this three. Okay? The flow rate, the speed, and the density. Okay. In the macros level. And then headway, yeah, is very important that you need to get this as your data. Okay. The others you can derive. Yeah. Okay. So what is flow rate? Yeah. So I use this pedestrian, but you can use the same for car. Yeah. So flow rate or volume is the number of pedestrian or vehicles, yeah, that pass an imaginary plane like this. Yeah, this one. Okay. Perpendicular to the line of sight. Okay. So, say this is your road. I will, from the top view. Okay. And these are your vehicles. Right. Say you are doing survey here. Okay. So, this, the line of sight is this one. Okay. So, that means if, this is important. Okay. If the situation is congested, okay, the vehicle does not move, what is the flow? what is the flow? In the congested, in the traffic jam, what is the flow? The flow is 0. Yeah, the flow is 0. Okay. So the flow rate, okay, when very crowded, the flow must be 0. Yeah, even though it has many people or it has many vehicles. Very important. Why? Because many what called traffic survey is wrong. Okay, they go in front. Say you are standing here. Okay, this is you. Okay, and then you see there is traffic jam. Okay, okay, and then you are counting the whole number of cars here. Okay, that is not flow. That is density. Okay, flow means the one that pass through your line of sight. Can you get this? Okay, if the car does not move, don't count. Okay, so N here is the number of pedestrian or the car that or the vehicle that pass through the line of sight. Okay, T is the observation time. Yeah, W here is the lane, or in pedestrian case, the width. Yeah, in car we use lane, so W here. Clear, yeah? So Q here is the flow rate or the volume. Okay. Then the volume, okay, when you have very small speed, the volume or the flow is 0. The same thing, if in the morning nobody is passing, yeah, only 1 or 2 passing, yeah, so high speed, okay, that is also free flow speed, yeah, the flow is also 0. Okay, yeah, this graph represent the speed and volume. Yeah? The bottom graph is density and volume. Yeah. So what we call as capacity is called capacity. That means flow capacity. Yeah. So that is maximum flow rate, not maximum density. Yeah. So this one. Okay. This one is the maximum flow. Yeah. That is capacity. Yeah, for pedestrian, typically around this value. Yeah. For car, typically around 1,800 to 2,500. Okay, clear? Yeah. For cars, yeah, in PCU, so I will put it this way. Yeah, 1,500. Yeah. PCU. Yeah, per hour per lane. Okay, until 2.5. Yeah, this is the typical value for vehicles. Yeah. Why I need to know the typical value? Because using that you can estimate, Yeah. So easier. So typical speed is also for pedestrian, this value. Okay. So yeah, this one. Lane capacity for vehicles, yeah. 1.5 to 2.5. I put it here already. Good. Clear or not? So when you put level of service, LOS A, B, C, D, E, F. Okay, A is around here. Yeah. B is around here. Yeah. C around here, and D is around here. Okay, so E, level of service E, is in the capacity. Yeah, this is level of service E in the capacity. Level of service F is below, very big, below capacity. Clear? Okay, so that means we are using the top region, yeah, not above capacity. Yeah. Below capacity is very big, it's all F. Yeah. So that's why we define congestion, yeah, congestion, okay, as Vc ratio, yeah, congestion equal to volume per capacity. Yeah. So congestion is basically volume per capacity, Vc ratio. Okay, that is congestion. You see? Okay, next, say if I have say in pedestrian, I will use area, yeah, because I have the length and the width, right? So then this is called pedestrian track or region of interest. Yeah. Easier if we assume rectangular, but not necessarily rectangular. And this is the example when I do pedestrian traffic data. Yeah, this is in Japan, in Flandong, in Sendai. Okay. So this is what I'm doing. So I get the top view camera, okay, and then I have the tile here, right? So there, the tile I get exactly one by one. Okay, we measure the tile and we draw exactly, and then from there we get the coordinate. And then each pedestrian I capture using camera, and then I create the program to track the head of each pedestrian. Then I can get the trajectory. Yeah? From the trajectory, I can get all the other traffic data. Yeah? It is from microscopic to macroscopic. Okay, so that means you need to get the pedestrian track. Yeah. How about if we use car? If you use car, okay, the A, okay, is just L times number of lane. Yeah? W here represent the lane. Yeah. Instead of meter, now you use lane. It's exactly the same, okay, the same concept, but instead of meter, now you use lane because the lane is standard, usually 3.5 meter. Right? One lane is 3.5 meter. Okay. Now, using that, you can get the flow rate. Yeah. So example, so say I got the pedestrian in this case, yeah, 480. Okay. And my observation time is 5 minutes. Yeah. And then the length is 1.5, but oh no, 1.5 is the width, the length is 2.5 meter. Okay, you don't care about the length, you only care about the width. Okay, so then you get the flow rate. Yeah, because this meter is meter of width, not the length. Yeah, this is how you define the flow rate. Yeah, in car, this width become lane. Remember, yeah. In vehicles, yeah, this width become lane. So The next traffic performance, important traffic performance is called density. Yeah, this is what people often mix up, yeah, between flow and density. Yeah, so they thought density is the one that you count. Okay, so density is the number of vehicles or pedestrian, okay, inside that truck. That means from the top view you take picture. Yeah, similar to this example. See, I put the snapshot, okay, and then I count the number of people in this particular snapshot. Yeah, if you use the drone, okay, you can get the snapshot. You can take the picture from the top, and then you get density. Yeah, and here represent the number of vehicles or pedestrian from the top view within that instant picture. Okay, and then divided by the area. Yeah, in this case, L times W. Yeah, remember, W is always the number of lanes in vehicles. Yeah, pedestrian we use W. Yeah, so for pedestrian, usually average density is about 4 pedestrian per square meter. Yeah, some people will say around can go beyond this. Yeah, but typically we use this one. Yeah. There is some study in Germany, they put military in one confined area, they can put 12 person in 1 square meter. Yeah, but very, very chunk. Yeah, but that's not normal. Normally around this value. Yeah. How about car? What is the typical density of a car? Well, what is the length of a car? Typically. Check you Google. Yeah. Can you search the typical width and the length of a car or bus?
Three,
3, maybe.
4 meters.
Yeah, between 3 to 4 meters. So in that case, you have the space in between. That means maybe half meter if it is top. Yeah. So half and half, that means you have 5 meter. Okay. 1 kilometer is 1,000 meter divided by 5. How much? Maximum density for vehicles, okay, if this their car, okay, so you will get around 200, isn't it? Yeah, so between 180 to 200, yeah, that's the typical density per lane, yeah, for vehicles, yeah. Car in this case. If bus costs longer, so in that case less. Is it clear? Yeah, based on the length, okay, so you can get the maximum density. Okay, the formula is easy. Yeah, the number of n in here is the snapshot from the top. Okay, and then divided by the area. So again, the same. So the same pedestrian trap here. Okay, but this time you use, yeah, you get 12 pedestrian. Okay, you use L and W to get density. Yeah, to get the flow, you don't use the L. You don't use the length. Why? Because by definition, okay, flow is the one that pass through the side observation line only, not the entire length. Okay? That's why width matter, not the length. Okay? But for density, yes, you use the length. Clear, yeah? So, yeah, so if the car length about 4 meters, yeah, space is 1 meter, so you get around 200, yeah. This is the typical value. Okay, up to here, is there any question? Can you distinguish between flow and density?
Okay.
Yes, please, Joshua.
Yeah. for pedestrians, if the I think would it be true also if the wind is also uh, going only one direction? But what if it's going uh,
Because this is per lane, so you need to get per direction. Per lane, per direction. No? Oh, for pedestrian, it's difficult because there is no lane, right? So in that case, you can get both. Yeah. For vehicles, you need to get it per direction, per lane, per direction. Okay. But for pedestrian, it's difficult to see the lane. Yeah. Even though there is some kind of self-organization to create some kind of lane formation, but it's difficult. So in that case, you can get both. Yeah. Yes, Ken.
Hi, sir. Question. You mentioned that for pedestrian it's quite hard, but would it be possible to to possibly use the area of an umbrella to signify the area occupied by a pedestrian?
Ah, umbrella is bigger than the actual person. Okay, so uh, can you measure from shoulder to from the left shoulder to the right shoulder? Can you measure how many centimeter?
No, I'm asking for an umbrella because here in the Philippines and in the tropics, it's raining quite frequently. So basically, the flow of pedestrians will be determined by an umbrella. So basically, the length or the diameter basically of an umbrella. Would it
Umbrella
be
is around 90 centimeter.
come
Umbrella,
again, sir?
umbrella is between 90 centimeter diameter, right? The diameter of umbrella
Around that, yeah, sir.
90 to 1 meter. Okay.
Yes.
In that case, the space become very light, not dense. So when we deal with pedestrian, okay, we are not just dealing pedestrian in walkway. Okay, you deal with pedestrian. The most dangerous part of pedestrian is actually why we need the maximum density. Because the most dangerous part of pedestrian is actually when there is a high density, and then people can get lift up and then stamp it. Okay, if you make it using umbrella, okay, probably you are talking about walkway on the street. That's fine.
Yeah.
Okay, that's probably fine. But when we deal with
Okay.
pedestrian, we are not dealing with that only. Okay,
Okay.
so you are dealing with the crowd, right? So when you deal with the crowd, you cannot use umbrella. Why?
Yes.
Okay, because people will get stampede because of your
Yes.
miscomputation.
Okay.
Okay, so for
Okay.
example, inside elevator, in the escalator,
Yeah.
or walkalator, yeah, and then within, even in the street, for example, within certain event, demonstration or some festival, right? So if you use umbrella, that's very dangerous. Why?
Yes.
You compute it wrongly, 90 centimeter, which actually become like squeezing like 50 centimeter only, half of
Okay.
that. Very, very big difference. Right.
Thank you, sir.
Yes. If you use it for convenience, for comfort, that's correct. Yeah. But not for the high density. Yes, Justin.
Sir, I have a concern when it comes to pedestrian data. Are duplicates of data should be concerned because pedestrians can come from either side of the traffic, right? Should that be a concerning factor when gathering your data?
Like this. I give you example in this picture. Right. So the whole width is here. Okay. But I only set the pedestrian tab in the middle. And then you are telling, how about people who is not passing in the trap? Should I still count? No. Okay. Because I take the sample. Okay. When you take the sample, then you consistently say, this is my sample area. Of course, you need to put the sample as representative as possible. But if I include this part, they are sitting down here. Okay. Then it is not representative of the actual things. Okay. Then there are a lot of things around here that is not represent the actual movement of pedestrian, then I don't include them. Okay. So once we set the pedestrian trap, so we consistently only take sample from there, not from outside. Okay. Otherwise, our sample become inconsistent. No? Okay.
Thank you, sir.
Yes. Okay. And nowadays with camera, you can actually get the trajectory, and then from there you can get the direction. Yeah. The same for vehicles also. Yeah. You can get the direction, the trajectory, and so on. Yeah, this is microscopic. Yeah. If you get the trajectory of person, we are dealing with microscopic level. Okay, anyway, let's go back here first. Once you have the flow and density, now we deal with speed. Okay, average speed. Now, in traffic flow theory, there are two types of average speed. Okay, one is called space mean speed, SMS. The other one is called time mean speed. So, which one we use? Okay. Space means speed, mean the average of speed for all pedestrian or vehicles occupying that track, occupying that sample that you use. Yeah. The observation track that you use. Yeah. For specific time period. So, in this case, space means speed depends on the length. Yeah. U depend on the length, okay, divided by the average of the time. Look at this. The time depends on when they go in and when they go out of that trap. So in the road, the same thing. Yeah. So this is the road. If you want to get the space mean speed, you set 2 points. Okay. And then when the vehicle entering this one, and when the vehicle going out of this one, yeah, in and out, and the time in, time out, okay, and then you minus, take the difference, and then you divide by the number of pedestrian or the number of cars, okay. So then you can get what is called space means speed. Is it clear or not? Yeah. And these are typical value for pedestrian, okay, around 1.2 normally. Yeah, for elderly around 0.9, 0.8. Okay. So now for vehicles, yeah, around 40, yeah, 30 to 40 kilometers per hour, right? In in normal road, if in the tollway, usually 60 to 80. Yeah, supposed to be normal range. Yeah, this is the space mean speed. This is what we use in the fundamental traffic flow formula. Remember, yeah, this is what we use in the fundamental traffic flow formula later. Yeah, so but there is another type of average speed, which is called time mean speed. Okay, the time mean speed, what is this? This is the average speed of individual, yeah, pedestrian or vehicles. How do you get this? This is get from the spot gun. So the police usually have spot gun, or maybe in the lab, okay, you have spot gun. When you use the spot gun, you don't get this one. You don't get the space mean speed. Okay, so if you use spot gun to get the average speed, okay, you cannot use that directly into the fundamental traffic flow formula. Okay, you need to convert first. Okay, so the TMS, the time mean speed, yeah, usually larger than the space mean speed. Okay, so be careful, yeah. Okay, if you are not familiar, usually you get the speed from spot gun. Okay, like the police. Okay, that is not what we use in the traffic flow. Yeah, in the traffic flow, what we use is this one: space mean speed, not time mean speed. Remember, yeah. So let's give you an example here. Say I have pedestrian trap. Okay, the length I put it 10 meter, and then the width is 1.5. Say I have only 3 pedestrian. Okay, and this is the time in and time out. Okay, so what is the space mean speed and time mean speed? All right, so what you will do? Yeah, you compute. Yeah, you take the time difference. Okay, and then you get the average of the time. Okay, so 12.5, 11.8, 10.5 here, divided by the number of pedestrian, yeah, 3. So you get 11.6, yeah. So the time mean speed, you will get 0. The length, yeah, the length depends on the length. That is 10 divided by this value, so you get 0.8. Okay, but if you use time mean speed, okay, you just simply get the speed. Yeah. So because you know the length, it is 10 meter, and you know the time, so you get the speed, isn't it? So that speed, if you average, it will not be the same. Yeah, close but not the same. Be careful. Yeah. What we use is not TMS, what we use is SMS. Is this clear or not? Okay. From there, you can get a formula. Yeah. So to get the formula, I use simplified method. Okay. The average travel time is the average of time of pedestrian or the vehicles inside that track. Yeah, the survey, the region of interest. Yeah. Then the observation time, okay, is the time that you use to observe, right? This is a sampling time. Okay? So in general, they are not the same. Okay, but if you set it the same, then you will get this fundamental traffic flow formula. Yeah. So if you set they are the same, the observation time is equal to average travel time. Yeah. Then you get, so you can remove the L here. Then you get this fundamental traffic flow formula. Flow equal to speed multiplied by density. Okay? Can you check the unit of this? Is this correct or not? What is the unit of flow? Yeah. PCU, passenger car unit, PCU per hour, per lane. Right? U is kilometer per hour. Yeah. K, what? PCU per kilometer per lane. Yeah. So this is called fundamental traffic flow formula. Okay. Using this, you can connect flow and speed and density. Yeah. This unit I put here is for pedestrian. Okay, this is remember, you remember this formula. Okay, that's why we call it fundamental traffic flow formula. This is very important formula. Okay, next, say if you have the average flow of 60, average density 1.25. Okay, what is the speed? Means speed. The space. This is wrong. Space means speed. Yeah? Space means speed. Yeah, the space means speed is just Q divided by K. Yeah, so you get very small. Yeah, 0.8. That is for old people. Okay. So for pedestrian, sometimes we use what is called pedestrian space or spacing. Yeah, this is called area module. It is just 1 over density. Yeah, sometimes we call it concentration. Yeah. So these are the graph between area module and the speed and the flow rate. Yeah. Usually, typically, something like this. Yeah. And this is the critical area, around 0.75 meters square per pedestrian. And in microscopic level, okay, you will have, for pedestrian, you have 2 coordinates, so X and Y. So these are the spacing between person. Okay. So in denser condition, people tend to reduce the longitudinal spacing. Yeah. Now, this formula here represents the microscopic level of, so S here is spacing, Q is the flow rate, U is the space means speed. Yeah, that means I connect between the macroscopic U and the spacing. Yeah, H here represents the headway. This is the time between consecutive vehicles or between 2 consecutive pedestrian. S here is the spacing. U is the macroscopic space mean speed. So this formula connect between microscopic and macroscopic. Yeah. S is 1 over K. Again, this is a spacing. This is a density. Yeah. This is micro level spacing. Density is macro. Yeah. So one of the important performance index is called headway. Headway, sometimes called inter-arrival time, or time between pedestrian, time between 2 consecutive vehicles. Yeah. The measurement of headway is actually the same as flow rate. Yeah. In the flow rate, you measure, okay, pedestrian or vehicle that pass imaginary plane perpendicular to the line of sight, right? So But instead of count, you check the time. Okay, the time difference, that is called headway. Okay, so for car or for vehicles, okay, usually around 1 seconds. Yeah, 1.2, 1.3. So in the intersection, this is what we count. Okay, headway. Okay, so if you have no, not 1 second, 2 seconds. Yeah, typical headway is around 2 seconds for a car. So in that case, 3,600 seconds per hour divided by 2 seconds headway. So you will get around 1,800, right? So this is normally the capacity, yeah, per lane. So the typical headway around 2 seconds. Okay. So you can also get the unit travel time, so tau here. Yeah. And this formula is relationship between the unit travel time, okay, and density and headway. The same thing, this one is the flow, unit travel time, and density. Yeah. Unit travel time is just 1 over u. Yeah. Tau here is the unit travel time, represent the travel time per vehicles or per pedestrian. Yeah. This is micro level. This is macro level. Now, having all of this micro level performance and macro level performance, okay, now we can connect, yeah, on the macro level with using a very simple model called Green-Shield model. So this is in 1935, very old. Yeah, I was not born yet. Okay, so yeah, this is before the war. Okay, so this assume a linear model between speed and density. Okay, so you have here UF here is the free flow speed, yeah, practically maximum speed. And Kj here is the jump density. Okay, this is where everything stopped. Okay, so then you connect with linear, yeah, a straight line. Okay, so in that case, you have two parameter, yeah, free flow speed UF and jump density Kj. Yeah. What is the typical free flow speed? Yeah, say 80, for example. Yeah. So what is the typical jump density? Maybe 180 to 200. So from there, okay, you can get the value. Yeah. Of course, you based on the data, you can use regression, okay, and then you can get the value of UF and KJ. Okay. So U is equal to UF, yeah, times minus, because this is negative slope, right? K is the density divided by Kj. Remember, yeah, Kj here and UF here are numbers, okay? While K and U are the variables, okay? So from here you can transform back and forth. Yeah, this is the same model. Yeah, I just transpose the density in the vertical axis and speed in the horizontal axis. I can get this one. Okay. Now, having these two, okay, now we connect with the fundamental traffic flow formula. Okay, this is the fundamental traffic flow formula, and this is the formula for Green-Shield linear model. Okay, so the Q here equal to U times K, but the U is already given here down. So I just input this U. Okay, I will get this formula, and if you multiply, okay, UF times 1 times K, so UFK, and then UF minus, yeah, UF times K again, so K square divided by Kj, right? So what you have here, this is a quadratic equation, okay? Remember, yeah, this is the function, functionally we write it this way, yeah? The flow is a function of K because UF and KJ are the parameters, yeah, numbers, okay? So if you plot, you will get something like this, yeah? So density and the volume, okay? So you get quadratic formula. So from here, what we will get? We get, I want to get this maximum. Why I want to get this maximum? Because this maximum means capacity, isn't it? Huh? This maximum volume is the capacity of the road. I want to get that. I want to know how to get the capacity of the road. That I keep telling this is around 1,500 to 2,500, but I want to get it from the data. Okay, so that means I need to get UF and KJ, and then from there I put it into this model. I supposed to get the value. Yeah. To get the maximum, of course, you take the first derivative and equate it to 0. Yeah. But Q is actually function of two, speed and density. So that's why we use partial derivative, yeah, not derivative, yeah. So this is easy. I just take the partial derivative to K. This is the K here. So then this K is removed. This 2 here going down there, right? So then you get this. Yeah. From here, you just put this is equal to 0. So this one is removed by itself because on the two side, yeah, left hand side and right hand side. So then K star, this is the critical density, is Kj per 2. Actually, this is easy to see. Yeah. So the capacity will happen at the middle, isn't it? Around the middle of density. Yeah. The same thing. So you can put the flow as a function of speed. Okay. You derive exactly the same thing. So Q is the function of speed now. Yeah. Remember, this speed is space means speed, yeah, not time means speed. Okay. And we can also derive, I want to get the capacity. What speed make the capacity? Yeah. Exactly the same. You get the first derivative equated to 0, and you can also have of maximum speed or the free flow speed. Okay. So with that, I can get the capacity easily. Here is the formula. Can you see? Okay. So if you have the fundamental traffic flow formula, yeah, Q equals U times K. A while ago we derived. Okay, you get the critical density and critical speed. Yeah. So you multiply the two, you get the capacity. Depends on your parameter. Huh? Okay. This parameter you can get from regression analysis. Is this clear or not? Yeah. So using this, you can get the capacity. This is how you get the capacity, Others, oh, how can I get the capacity? I get only the flow. Yeah, well, you need to get the flow and the density, or the speed. I need two of them, and then you can get this value. Yeah. Okay. So typically the capacity, this value. Yeah. Okay. Let's take example here. I use data. Yeah, for pedestrian. Okay. Later for car, you do it on your assignment later. Yeah. Next week you need to submit that in Moodle. Okay. So say I have this density and speed data for pedestrian. Can you use green shield model to compute the maximum density, maximum speed, and the capacity? Oh, how to do that? So if you have this data, what you will do? You will get a regression analysis. Yeah, we already discussed regression a while ago and last week, right? Okay, you get the slope and the intercept of this data. Yeah. Okay. Did I connect the dot? Okay. So once you have the slope and the intercept, okay, so this slope represent minus UF per kj, and the intercept is the UF. In that case, you can get the kg, right? And then from there, you just multiply, yeah, with 1/4 UF times kj, so you get the capacity. Wow. Okay, you can use data. Okay, once you have the either speed and density, or the flow and density, or flow and speed. Okay, any two data, you can get the regression, and then you can use the model, and then you can get the parameters, yeah, the slope and intercepts, and then you can get the UF and KJ, and then you can get the actual capacity. Cool. Any question? Okay. So once you have this, what you will do? Oh, we have the capacity. Okay. So if you have the capacity, you have the volume, yeah, or the Q, yeah, and then you divide it by the capacity. Yeah. In this case, I use C. Sometimes we use Phi-C ratio. This is exactly the same, yeah. So this is the volume divided by capacity. Okay. So this is congestion, isn't it? Okay. So if you have this, so I just write this in terms of Phi-C ratio. And so I have the Q, this is the flow, I have the capacity. Okay. Okay. From there, I can compute algebraically, and I get these things in yellow. Yeah. What's the meaning? That means the Phi-C ratio or the congestion, yeah, depends on U. Yeah, it's a function of speed. Yeah. Okay. Of course, I can also do reverse. Okay. This is the derivation. Yeah. I can do the reverse. Okay. Using the Phi-C ratio. Okay. I can solve that using quadratic formula. Okay. And once you solve that, okay, then I can get the actual speed, right? Speed, okay. Because this is quadratic, so you have a plus and minus, right? So if you solve this quadratic equation, you get this quadratic formula, okay? And I don't use the bottom part here. This is level of surface F. So I use only A, B, C, D, E. So in that case, I put plus, yeah, the sign. Yeah. So what is this formula about? You use speed is a function of congestion. You have the speed as a function of congestion. Of course, you will need to have the parameter here, which is the free flow speed. Yeah. So if you already know the length and you know the speed, can you get the travel time? Yes. Yeah, easy. Okay. So the travel time is just length divided by the space mean speed, isn't it? So in that case, I just define, yeah. U, this is the formula a while ago, right? So now I have the L is the length. So then I divide by U. U is this one. Okay. Then I will have the formula to get the travel time. Oh, what is this? The travel time is a function of L. L is the length. Okay. And the PC ratio, this one, yeah, the congestion. Yeah. So if you plot, you will get this kind of plot, yeah, the one in orange here. Is it clear or not? So what will happen if congestion is exactly 1? So these are 1 and 1 is 0, right? So 1 minus 1 is 0, right? So then travel time is L divided by mu F. Okay. So it's asymptotic. What happens if the congestion is larger than 1? It's possible congestion larger than 1. What's the meaning of congestion larger than 1? I thought it's something divided by maximum. We cannot divide something divided by the largest, right? Yeah, in green shield, you cannot have that because if the volume is larger than the maximum, this one become negative, so become irrational number. Okay, so the congestion cannot go beyond 1 in green shield. But in reality, remember in this deriving this formula, I said I don't use this part. You see, I don't use this part. But in reality, sometimes we go beyond this, yeah, above this congestion, isn't it? So beyond 1 in that case. Yeah? So how about the one in this region? Yeah. So in that case, you cannot use green shield, yeah? Or you can use, but you need to use the minus part here. Yeah. So you need to modify the green shield. Yeah. So in 1964, okay, Bureau of Public Road in the US, okay, proposed different function, okay, between travel time and congestion and U and UF like this. Okay, so what they use is T equal to T0, okay, multiplied by 1 plus gamma multiplied by congestion. So this one, I will put G, yeah, and then exponent to eta. Yeah. So this one is equal to mu f. Is that correct? P equal as okay. So T is equal to L divided by mu F. Okay, so 1 plus gamma is typically 0.15. Okay, and then G is still G in here is congestion. Exponent 4, usually the eta is 4. So this is what we use. This is called PPR formula. And we will use this a lot later. Yeah. So you can use either this formula in green seal or you can use the PPR formula here. Please record this. Okay. Any question up to here? So what we are doing here, we are deriving the formula, okay, to connect between travel time and congestion. Yeah. So we connect between travel time and congestion. Yeah, meaning the cost. Travel time means the cost, right? So you connect the cost and congestion. Yeah. Okay. Any question? So, okay, so I have the length 100-meter escalator. So we have maximum density for 5 pedestrian per square meter. Okay. And then the maximum speed, very small. Yeah, 0.7 because escalator is a machine. Okay, what is the average travel time? Yeah. So if you use this one, if you plot VC ratio and travel time, you will get this plot. Yeah, this is the typical clean sheet. Yeah, pedestrian usually linear, so we can use clean sheet. Okay, so look at this is important. Look at the value here above 0.75. Yeah, if congestion above 0.75, can you see that this is start to separate from the linear model? Yeah. So that means the delay, this area represents the delay, Yeah. Yeah. So the larger it is of the congestion, clearly closer to 1, okay, the travel time become nonlinear, very big. Okay. So congestion is or the travel time is nonlinear. Okay, with the connection of congestion. So that means suppose you are here 0.85. Okay, if you can reduce the congestion by just 20%, say it becomes 0.6, for example. Okay, so then suddenly disappear, the congestion disappear. Okay. Similarly, if you are already in the congested region, so it's 0.8, and then adding just a few percentage, suddenly the congestion become very severe. Okay, so this is non-linear phenomena. Okay, so and this value 0.75 around, yeah, around 0.8, 0.75. These are the typical value that we see that they are starting to depart, yeah, from the linear model. So these are critical value that we use, yeah, to decide, oh, this is congested, or this is not congested, like that. Yeah, for rule of thumb. Okay. So can you uh, can you practice if you want? So what is the function between the congestion efficiency ratio as a function of average travel time? Yeah. So I want to get this. Yeah. Congestion as a function of average travel time, T. Yeah. So in this case, you can calculate. Yeah. This is the result. We use a new variable z. It's computed based on this value. Yeah. So this is the way to derive that formula. Yeah. So we can connect the congestion with travel time, yeah, using green shield. Okay. You can also connect this with the space capacity. Yeah. Space capacity is the number maximum. Yeah. This is the jump density. So maximum number of people who can be accommodated in the space in the pedestrian track. Yeah. So sometimes space capacity is more appealing than flow capacity, yeah, especially for pedestrian, because it's easier to measure physically in the static condition, yeah, using camera. Yeah. So the relationship you can derive on your own. So the slide consists of the derivation. So you can get this value. Yeah. And in general, okay, the ratio of the number of pedestrians over its space capacity is actually the same, yeah, as the ratio between the density and jump density. Yeah. Say I will keep new symbol here, zeta. From there we can derive, yeah. We can derive the volume per capacity ratio and then connect it to zeta. Okay. So yeah, maybe I'm not sure if this is important for you, but at least you know the formula. So in case you need to use, you don't need to derive it anymore. So I just provide it for you. Huh? So if you have the zeta or the space capacity, you can also connect it to travel time. Okay. Okay. With this, you can do the assignment. Yeah, in Moodle. Yeah, green shield. So you can use in Excel. Okay, green shield formula. So please use the green shield formula. Okay, you can set your own free flow speed and the jump density, yeah, in two separate cells. Yeah, and then don't forget to draw the diagram. The diagram I already show in the slide. Yeah, if your diagram does not get like that, means something is wrong with your formula. Remember, yeah, typically the one that make mistake is you forget that density or the speed is actually function of density. Without that information, you will not get the correct diagram. Okay, so do this, yeah, get the flow rate versus space mean speed, flow rate versus density, density versus space mean speed, and then you identify the critical speed, critical density, and then from there you get the link capacity. Yeah, is that okay? So until next week, this one. Okay, any question? Okay, so in that case, we are almost time. Okay, so please next week can you read this two, yeah, policy analysis and network flow identity, yeah, and then we will do the workshop. Okay, these three we will do it next week, and then next week we have another assignment here. Okay. Question? Discussion? We still have 3 minutes. Everything clear or unclear? What did you learn? Give me feedback. Yes, Ken, you want to say something? You are still.
Sir, hello.
Yeah.
Yeah, basically no questions on my end, but basically my biggest takeaway for this lesson is with the transformation, the computation using matrices. So that's one of the biggest lessons that I've learned today.
Okay. So can you see that from the regression, you can get the capacity? Okay. From the regression formula, okay, the transformation that you do, you can actually get the capacity of a road. That means you can get the data, okay, and then you can get the actual capacity. It's quite difficult to get the capacity. People will say, oh, I use highway capacity manual. Yes, but have you ever asked yourself why I use that standard, which is from the US, not in the Philippines, and how are you going to use it for your own? Okay. So this lesson telling you, look, I can create my own standard because I know how to compute capacity. Isn't that awesome? Right? Okay. Because situation there is not the same as here, right? Then why should you use other people's standard? You can use your own city standard. Okay, maybe in different type of vehicles, there is no chimney there in the US, right? So different behavior. So in that case, you can do. I hope this is useful, yeah. And the connection between travel time and the congestion, we will use it again and again, especially the PPR formula a while ago. Okay, with this, thank you very much for today. So see you next week. You have assignment, don't forget to do it, yeah, and claim your recitation for today. Yeah, some of you who have claimed, so I already graded in Moodle. Yeah, those who forget to claim, when you attend, you just claim, you get 1 point. Even if you don't say anything, you just claim. Okay? Good. So see you next week.
Thank you, sir.
Thank you, sir. Thank you, sir.
Bye.